Ryan, please let us know once we can start.
I think you can start now. We're live. Krishna.
Okay, wonderful. Hi, everyone. Welcome to our tutorial on responsible AI in industry. My name is Krishna Ram Kentapadi. I'm a principal scientist at the Amazon Web Services AI team, leading privacy, fairness, explainability, and model understanding efforts in the Amazon AI platform. Along with me today is Nashli Sifas. Nashli, why don't you introduce yourself?
Hey everybody, I'm Nashli Cephas, and like Krishna, I work for the AWS AI team. I'm focusing on fairness and mitigating biases in AI technologies. And so, thank you for joining us today. We also have two other presenters. That one will be via video, and another will be uh, won't be able to make it today. But we will carry on, and please feel free to put any questions that you have into the Slido. Use the hashtag. I believe it's, let me, actually, I don't know what the hashtag is. Hold on, let me see if I can find a hashtag. But we will be taking live questions from the Slido and asking and interjecting throughout the presentation. So feel free to put in questions at any time, and we'll make sure that we have those to you. So you will be using the hashtag. Uh, I'll post it in the Zoom. I don't know if you know it or if anybody else has it.
So I think they know it. Like if you go to the fact web page for the attendees, all the information is right there. So the Slido link, everything is there over there. So in this tutorial, we will focus primarily on the three dimensions of privacy, fairness, and explainability. And to give some context, prior to this tutorial, we had presented similar tutorials on privacy, on fairness, and on explainability in industry settings. In particular, I would like to thank Timnit Gebru, whom I had reached out a couple of years in the past to find out potential collaborators from other companies. Timnit then connected me with Meg Mitchell, with whom we had co-presented a tutorial on fairness-aware machine learning in industry. What we found that even though we were from different tech companies, we all had similar experiences and similar lessons learned while applying responsible AI techniques in practice. So today we will present case studies from Amazon, LinkedIn, and Microsoft. Please refer the longer version of our tutorial for additional case studies, especially the case studies from Google, which we would not be able to present today. And the longer version is available at the link mentioned here, the sites.google.com/view/responsible AI tutorial. So let's start with going back nearly 2 decades. So this was at the time back in 1997 when William Weld was the governor of Massachusetts, and Lawton Sweeney was a grad student at MIT. Back then, the Group Insurance Commission of the state decided to make the medical history of state employees available for research purposes, and they took measures to anonymize, remove identifying information such as names, address, phone number, social security number, and so forth, and then made the anonymized version available for research purposes. And what Sweeney did was she purchased the voter records of Cambridge by spending about $20 and getting a diskette of the records. And she was able to join the so-called anonymized medical data with the voter records, not on attributes like name, address, and so forth, but on attributes such as zip code, date of birth, and gender, and was able to identify the records of William Weld, who was the governor of Massachusetts, and also confirmed that she had identified the right records because William was a public personality. So at first it might seem like this is an isolated incident, but turns out that this is not the case. later research has shown that for about 2/3 of the US population, they are uniquely identifiable based on a small number of combinations of small number of attributes. So this example highlights that it's very important to think through rigorous ways for protecting privacy in datasets rather than resorting to ad hoc techniques. Let's fast forward nearly 2 decades later. Over the last several years, we have seen several incidents of biases across a variety of applications, ranging from photo tagging to web search to criminal justice, lending, hiring, and so on. And almost every day or every week, we hear such instances in the media, in research practitioners community. So for this community, it's quite evident why this is happening, and there has been a lot of very nice research and even popular books going into the ethical challenges posed by AI and machine learning systems. As we all know, there are several types of biases present in society, and often these biases may be reflected in the training data or in the model optimization constraints and so on. And it's not at all surprising that AI models are prone to demonstrating such biases in some cases. At the same time, there have been a number of regulations and laws against different forms of discrimination. For example, in the United States, many of these regulations uh, are, are related to the Civil Rights Movement and Civil Rights Act of 1964, which prohibits discrimination on the basis of attributes such as race, sex, and so forth. More recently, we have seen renewed attention on these uh, topics because of recent regulations such as the European Union's GDPR, as well as subsequent regulations like California's Consumer Privacy Act. At first,
Hey.
uh,
Oh yeah, so I just wanted to chime in that I think it's also this right here highlights that the issues around fairness and biases pertain to more than just the technologies. This is on a larger scale. There's a lot of stakeholders involved, government, policymakers. This is international. There's global concerns, and everyone's seems to be on a different page. And so I think that is just as important as understanding how us as technologists can improve the technology, improve accuracy, improve fairness and biases in data. But the conversation is a broader conversation that needs to be had. So thanks for pointing that out, Krishna.
Yeah, thanks, Ashley. That's a very important point. This is a message that will come across in the tutorial that this is not a purely technical problem. This is as we all know, this is a socio-technical dimension, and it requires involvement of all stakeholders, not just people with technical background like the presenters in the tutorial, but also people from policy, legal, yeah, and other stakeholders, social science and so forth, as well as the end users and communities themselves who are potentially impacted by these technologies. So specifically, like going back to these regulations, at first it might seem like these regulations are primarily about privacy, but if you look closer, they also discuss related notions like fairness, transparency, and explainability. So let's look at a little bit more about explainability. Why is this important? There are at least a few different motivations. We already saw the regulatory motivation. Often it's important to understand why a machine learning model made a given prediction, and also whether that prediction is free from biases, both at the time of training and at the time of inference after the model is deployed. There is also a similar motivation from a business angle, wherein often data scientists or other practitioners may want to provide explanations to various internal teams, such as loan officers, compliance teams, customer service representatives, and so forth, and sometimes even to the end users or the customers of those the technologies. The third motivation comes from a data science and machine learning angle, wherein data scientists may want to understand which features are most important or which parts of the data contributed the most and so forth. And they would want to improve the model over time. They may want to understand what are the failure modes of the model, what are the cases where the model cannot be relied upon, so that we may have to make use of domain experts. How do we debug the predictions of the model and so forth. So for many of these angles, notions like explainability and transparency are equally important. So if there is one takeaway from this tutorial, it's that we need to think of notions like privacy, fairness, and explainability in machine learning by design, as opposed to viewing them as an afterthought. Let's briefly look at some of the challenges that we face when we apply these techniques in practice. I'll give two motivations. First is the motivation of say a large cloud setting. Specifically here, I'm showing the AWS machine learning stack. At the bottom, we offer various frameworks and infrastructure. Such as TensorFlow, PyTorch, MXNet, as well as deep learning containers, machine images, and so forth. This is targeted for the most sophisticated or most sophisticated customers who may want to build their own machine learning pipelines and be willing to have a lot of customization and control over what they want to do. At the middle, we have uh, Amazon SageMaker, which is a managed service to help data scientists and ML practitioners to obtain training data through labeling, to train models, tune models, deploy models, monitor models, and so forth. And at the top, we also offer various AI services, often related to cognition tasks, such as yeah, object or image recognition, or translation, or text to speech, speech to text, personalization, or fraud detection, chatbots, and so forth. So if we consider these layers, there are different types of challenges. Uh, First challenge is, how do we provide functionality for privacy, fairness, or explainability that caters to the needs of customers across a broad range of industries, ranging from regulated industries such as financial services, healthcare, hiring, and so forth, as well as to other broader industries like manufacturing, or even like sports, or understanding about climate change, and so on and so forth. So that's the first challenge. The second challenge is, even if we select one specific industry, such as financial services, the requirements of large banks may be very different from the requirements of startups or smaller entities. In turn, may be different from the requirements of, let's say, regulatory agencies. So that introduces another types of challenge. The third is the challenges that we face at the layer, such as the machine learning services or Amazon SageMaker, may be quite different from the challenges for specific application verticals, like healthcare, or vision, or speech, or anomaly detection, and so forth. So this is one type of scaling challenge. How do we scale tools for fairness, explainability, and privacy across many different customers, many different types of customers, and many different layers or abstractions of machine learning and AI services? The second type of challenge arises in a relatively complex machine learning setting. So for this, I would like to use my LinkedIn as an example. I used to work at LinkedIn, so I have a lot of familiarity with this setting. Nashik, go ahead.
Yeah, so this is great. We have a question that came in. I just wanted to pose, and I can also assist in answering this question as well. But this question is from Jahio Chen. It says, do you see generalizability of concerns of fairness, explainability, privacy, etc., across multiple industrial sectors? They also ask, Financial services have very specific requirements, for example. So in terms of general concerns across all these topics in multiple sectors, yes, I would say there are definitely some that can be generalized. I mean, in overall, the concern is that, you know, people will be limited to certain privileges. People's rights will be infringed. People feel that they may be marginalized, in a way that, you know, isn't that they actually may be harmful to them. And so, however, some of those industries are not as quote unquote mission critical as others. And so we do place, you know, top priority on all the concerns, but especially the ones that are mission critical that put people in harm's way. There are some specifics that you can go into to try to resolve some of those as well. So I don't know if anyone else wanted to chime in, Krishna or Rush.
Yeah. So thanks, Ashley, and thanks, Joe, for that very relevant question. So to add to what Ashley said, there are definitely like commonalities across industries. For example, yeah, irrespective of the industry, often it is desirable to ensure that the model has similar predictive behavior across different groups of interest, across different genders, race, age groups, or their combinations, and so forth. For example, we may want to ensure that the model has very low false positive rate or similar false positive rate across these groups. But at the same time, as you pointed out, there is also differences by industry. In financial services, there are very specific regulations, and that's what makes this problem more challenging. And as we will see later when we go through the Amazon SageMaker Clarify use case and demo, we'll see that some of the bias measures are chosen based on these regulations to map from what is mentioned in the regulations from different regions and what customers care about to the specific bias metrics. So the short answer is yes, there are definitely domain specific requirements, and that makes this problem a little bit more challenging and also interesting. All right, so let's look at the second type of scaling challenge. If you consider and a setting like LinkedIn, as you all know, LinkedIn operates the largest professional network on the internet with more than 500 million members, several tens of millions of jobs and companies, tens of thousands of skills, schools, and so on. If you take a setting like the feed ranking of LinkedIn, so that itself is powered by several models corresponding to, let's say, people recommendations, job recommendations, ads, and other news and other types of updates. And if you take any one of this, if you take, say, let's say, job recommendations, that the model for the machine learning model for that itself makes use of earlier models which map a member's a title to a canonical title, or a model that maps a job's title to a canonical title, or a model that extracts skills from a member's profile, or just skills from a job posting, and so on. So in such complex systems, often we see a sequence of machine learning models which are chained. So one challenge here is, how do we reason about, let's say, fairness of the system as a whole? Or how do we reason about the explainability or providing explanation of the final user-facing aspect of the system? Given that some of these machine learning models are hidden or they're kind of lower in the stack, how do we reason about privacy of this composite system in terms of privacy of the individual systems? Amongst even these three dimensions, in some of these, there are better understanding. We have better understanding. For example, we know that with the notions like differential privacy, there is composability properties. and differential privacy is robust to arbitrary post-processing. But if you consider, say, fairness, there are some flavor of negative results on composition of fairness across models, and there is a lot of recent research on understanding how we reason about composition of fairness. Similarly, even with explainability, there are a lot of interesting open challenges around how do we reason about or provide explanations of such a composite system. So this is another type of challenge. So with this context, in the rest of the tutorial, given the limited time, we are going to focus on a brief overview of several responsible AI tools. Then we will go through a few case studies across LinkedIn, Amazon, and Microsoft. In fact, the Microsoft's case studies will be included in the tools discussion. And then we will conclude with a few key takeaways. If you are interested in an in-depth overview of each of these topics, fairness, explainability, and privacy, please refer the longer version, which is present on the tutorial website. We had presented a longer version at the recent AAA conference, as well as there are a number of related tutorials which are also linked from the conference, from the tutorial webpage. With that,
So I'll just add that we'll be wrapping up with a lot of great practical resources here, and we do have one additional question before we hop into the tutorials. So this question is from Christian Lopez. So right now, some industries have been trying to use data science, especially exploring machine learning ops. But how can we be agile and have models using responsible AI? So yeah, the machine learning ops, I think, is that I'm assuming that is, the management and the deployment of the model into production.
Yes, so I think I can touch upon that. I think that's also a highly relevant question. So just like DevOps, which is traditionally for code and traditional software, recently there is an intersection of machine learning and DevOps. It's called machine learning ops or machine learning operations, wherein just like in traditional software engineering, you would want continuous integration, continuous deployment, CI/CD of machine learning models. And it's not just enough that you look at or analyze the behavior of models during model training, but also monitor them once they're deployed. The reason about fairness or bias of the models once they have been deployed, or other properties, whether there is a drift in the data, or drift in concepts, or drift in the other types of changes in the underlying distribution, causing the model to behave in a manner that's not expected. I think this is a very much evolving field. And again, we will briefly cover some of these aspects of things like monitoring a deployed model for any biases as well as for change in the explanation properties of the model.
I can also chime in real quick.
Sure.
Let me also turn on my video. Okay, so many of the toolkits that we're going to cover in the later portion of this talk, which is relevant to what is out there specifically in the open source, they are open source and free to use, and of course available to everyone. So you will see some of them are having very, very clear API structure as what parameters you need to pass to them. For instance, in case of fairness assessment, it might be you pass the sensitive attributes, you pass the favorable outcome, you pass the model object, etc. So I am very positive that using this variety of open source toolkits like interpretability toolkits, open source, fairness toolkits that are open source, etc., you can just translate their inputs into either a YAML format or something, and then kick off these tools via very seamless workflows throughout your ML lifecycle. So imagine you have a machine learning training pipeline, and one aspect is actually the step that is training your model. That can be followed by the fairness assessment, which gets fed through passing the model object, passing the sensitive attributes. And so you can orchestrate them all after each other just with use of these open source toolkits that we will cover in the next portion of this talk, and use that in your DevOps for machine learning or ML ops both during the assessment time and with some tweaks during your monitoring time as well. So I really recommend staying tuned for that portion and taking a look at the toolkits that are out there and see how you can incorporate it seamlessly in your DevOps pipeline back to back after your model training or model deployment process.
And Marnoosh, I know we gave quick introductions at the beginning. I don't know if you want to give just a really quick introduction before we hop into the tutorials.
Sure, absolutely. Sorry I was late. My name is Marnoosh Simeki. I'm a senior technical program manager at Microsoft, and I drive the product efforts behind some of the open source toolkits that we have, like FairLearn, Error Analysis, and Interpret ML, and their integrations with our Azure Machine Learning Cloud. And yeah, please, I'll stay tuned and I'll stay here. And yeah, any questions, I'll be also happy to chime in. Thank you so much.
Thanks, Marnoosh and Nashley. So in the interest of time, let's perhaps maybe defer questions to the end of each section or towards the end of the talk. And we will be more than happy to respond on the Slido as well, either during the tutorial or right afterwards. So please stay tuned. So let me play this part, which is about.
Hi everyone, my name is Marnoosh Simeki, and I'm a senior program manager at Microsoft, driving some of the product efforts behind our responsible AI tooling, Interpret ML, FairLearn, and Error Analysis. And today I'm very excited to walk you through some of the AI fairness and transparency tools, starting with our own Microsoft tooling. And so something that I want to highlight here and was highlighted as a part of Krishna Ran's talk was interpretability, transparency, and fairness are super important parts of understanding your model, not just during training time, but also at inferencing time. During training time, because data scientists require tools to explain the output of models to stakeholders, the business stakeholders, users, clients, and also they need tools to debug and assess their models and make informed decisions as how they should improve it. Without having such tools to help you understand what is going on inside your model's decision-making process, there's really, really little info on how you can improve your models. And eventually, data scientists require tools to verify if models' behavior is matching some pre-declared objectives that probably some domain experts and some expert stakeholders have identified. For instance, if you're working in the space of financial services, or if you're working in the space of healthcare, doctors or physicians or financial experts might have some insights that they're sharing with you regarding the nature of what you're fitting a model on. And so it would be great to fit and to sort of assess whether that model has made predictions based on those insights that the experts are sharing with you. And eventually I'll add and open a parenthesis here regarding the fact that transparency is super connected to fairness because it can act as a proxy into the world of fairness. And if you understand that many important factors that are impacting your model predictions are sensitive factors like age or gender, etc., then you know that you have an issue that you need to go and resolve and improve the fairness of your model. And eventually, such tools are super important during inferencing time because they can really help you build trust with your users. It would be very helpful sometimes to provide the answer to a lot of why questions, why my loan got rejected. And also providers of solutions to end users, like the physician who is getting an insight from the model and wants to take an actionable item based on that or actionable decision based on that. They're required to know how the model has made prediction and whether that makes sense based on their medical knowledge. So within Microsoft, we have worked on an interpretability toolkit called Interpret ML, which is helping you to understand and debug and assess your machine learning models. And this is an open source package. So if you go to github.com/interpretml, you will find many packages being represented underneath that. And today I want to briefly walk you through what those packages are. The first one is called Interpret, which is accompanied closely with another one, which is called Interpret Community. And that includes a collection of either intrinsically interpretable models or black box explainers to help you understand and uncover what's going on inside your model's decision-making process. That is geared towards tabular data. So regular classification, regression cases, and scenarios that are trained on top of tabular data will be well supported by these two packages. Interpret text is also sort of an add-on for text scenarios, starting with text classification scenarios. So if you are having any text classification scenario and you're interested in understanding which words inside the sentence are making the prediction and classification of the text in one way or another, that would be a package that you would like to check out. Eventually, there is diverse counterfactual explanation, which basically means what are the closest data points with different outcomes, or in other words, helps you understand what is the minimum change that you need to apply to each individual data point for the model to produce a different outcome for it. The insights might be Marnoosh's loan has got rejected. The closest data point to Marnoosh's loan with approval on his or her loan is Anna, and that person, Anna, is earning 5K more than Marnoosh. the other factors more or less are the same. So let's dive a little bit deeper. So inside an interpret community, there are a collection of glass box models, which are intrinsically interpretable models. We have a state-of-the-art model called Explainable Boosting Machine, which actually enables you to basically get lossless explainability. No approximations are happening there. That opens your model, and that is an intrinsically interpreted model. So the great thing about Explainable Boosting Machine is it is very, very accurate, but yet super transparent and interpretable. So I'll definitely recommend for those of you who are interested in giving a state-of-the-art intrinsically interpretable model a shot, Explainable Boosting Machine, or short EBM, will be your best friend. Now, in case you have your own models and you want to use approximations on top to uncover how that model has made its predictions, we have brought all state-of-the-art third-party and Microsoft-grown interpretability techniques under one roof with the same set of APIs and also a visualization dashboard. And we enable you to run that on top of your model and see how the model has made its predictions. The second toolkit that I would like to briefly introduce is our FairLearn toolkit, or Fairness Assessment and Unfairness Mitigation toolkit. And that is inspired by the fact that there are many ways that AI systems can behave unfairly. Some of my co-presenters walk you through the concept of fairness in AI, but I would like to highlight that FairLearn in general looks at two different types of harms that are really commonly and widely happening in the space of AI system model training. The first one is harm of quality of service, where your AI system is providing different quality of service for different groups of people. And an example of it is when a voice recognition system might fail to work as well for women as it does for men. So the same AI system works better for one group of people as it does for another group of people. The second class of harms that we support within FairLearn is harm of allocation. And that's when information, resources, or opportunities are allocated differently among different groups of people. And an example of it is it's either a loan scenario or, say, job application scenario, where a loan or job application scenario might be much better at picking good candidates among white men compared to other groups. And so the question really comes down to, can we truly assess some of these fairness issues and avoid negative outcomes of AI systems for different groups of people? And that's what FairLearn is hoping to address. FairLearn is hoping to help you assess the fairness of your machine learning models. We provide a set of common fairness metrics and an interactive dashboard to assess which groups of people may be negatively impacted. It supports, similar to interpretability, Python models that have been trained either using scikit convention or any deep neural network model trained via frameworks like PyTorch, Keras, and TensorFlow. The other thing is we support group fairness, and we have 15 plus common group fairness metrics that you can use in order to understand how your model is making these predictions. And eventually, at the moment, both our interpretability solutions and fairness assessment and unfairness mitigation capabilities are supporting classification and regression models. Eventually, we have fairness mitigation algorithms, which are state-of-the-art. A lot of them are from Microsoft Research New York City, that help you incorporate some unfairness mitigation policies or techniques inside your machine learning lifecycle. And some of them are like post-processing methods, which sit on top of your model predictions and get a fairness criteria and help you basically reassess or readjust some of the predictions to meet that fairness criteria goal. And in some other cases, there are more, I would say, in-processing, pre-processing techniques, which enable you to relabel and reweight your training data and retrain your machine learning model based on, again, a fairness criteria. And that hopefully helps you get a better and more accurate and more fair machine learning model. And so both of these toolkits actually come with interactive visualization dashboards. And before diving deep into one example, I would like to highlight two scenarios of two customer cases that we've done successful pilots with these tools. And one is an exciting case study in the healthcare space with Philips Health Team Care, which basically collects a huge amount of data from ICUs to benchmark ICU performance. And so they used FairLearn to check that their models perform similarly for patients with, say, different ethnicities and gender identities and any other sensitive attribute groups. And this customer engagement was briefly mentioned at Microsoft Ignite, but please stay tuned for a more, a deeper investigation and like a case study with us pretty soon. And the other one that I'm going to highlight, and we're going to see a similar demo to the goal of this study, was with Ernst & Young, and they were actually working with real banking data. And what they were interested in was using FairLearn in practice for financial and loan allocation scenario. And the situation was they had a lot of signals or a lot of features that were sensitive, and they wanted to make sure that the loan allocation scenario is not being impacted in any form or shape by these sensitive attributes. And while they were removing the sensitive attributes during training time, we all know that some other factors can act as a proxy and leak information into your model training lifecycle. And so it is super important to bring them, even if you're not using your sensitive attributes during training time, still bring them to assessment time to make sure that no other factor has acted as a proxy. And so today I would like to highlight one case study regarding the loan allocation scenario. The example that I'm going to highlight is basically on a loan allocation scenario with, I'm using the traditional census data with 32K individuals predicting the annual income of above or below 50,000. But just for the sake of demonstration and this demo that we're doing together, I'm going to treat that label, that output label, as approval or rejection on the loan. And so the very first thing that I am going to do is I am going to get my data set and identify what are my sensitive attributes, in this case, sex and race. I'm going to split it into train and test, and I'm going to apply some feature transformations, for instance, one-hot encoding on top of my categorical features and standard scaling on top of my numeric features. And so my model training pipeline becomes applying these feature transformations and feeding my classification model on top of my data. And eventually, that's where our interpretability techniques come into the scenario. Here, I'm calling SHAP kernel explainer that we wrapped under interpret ML. I'm passing the model object, which is basically being taken from the last step of this pipeline. Hence, you see that last step, take the model object. The other parameters that I'm passing are training data, the name of the features, name of the classes. These are actually optional, but they really help you in the visualization dashboard, as we will see together. For the readability purposes, it's important to pass them. Otherwise, you will see the feature importance values in terms of feature 1, feature 2, feature 3, which the mapping later will be problematic a little bit for you. It's going to be more difficult to read it as a human with no labels. And the unique part to this package that we wrapped is we enable you to pass your feature transformation pipeline. So here, if you remember, I had a feature transformation pipeline, and so I'm now passing it. And so that enables my explainer to reverse the feature engineering pipeline for me and return the feature importance values in terms of raw features rather than engineered features, which otherwise sort of defeats the purpose. If you see the feature importance values in terms of engineered features that are not that human readable, I think that would not be as beneficial as you can see the feature importance values in terms of human readable raw features that you really send to your model. Four tabs: model performance, dataset explorer, global explanation or aggregate feature importance, and local explanation or individual feature importance and Whatif. And so what I did was I also have defined 2 cohorts of female group and male group, just so because we want to sort of see whether the model is treating different binary gender groups the same or not. And so right off the bat, I can see that how the model is performing on females compared to males. I can see that this is a box plot with like median, 25th percentile, 75th percentile, and then the x-axis we have probability of rejected that the model has predicted basically. And so you can see that for female group, the median probability of rejected is way higher than the male group. And the size of this box plot, the fact that it's smaller, it's shorter, it says that the 25th percentile and median and 75th percentile are closer to each other. And so systematically, women are receiving higher rejection rates. I am very curious to see whether I represented qualified females well in my data set. And so I come to Dataset Explorer, set it to ground truth values, and I can see females, what percentage had the ground truth of rejected versus approved. How about males? And so I model. But before going to any mitigation phase, I would like to also highlight that you can see, first I'm going to turn this off, what are the top key important factors impacting my model predictions. It seems like marital status, education, occupation, capital gain are the top 4 important factors impacting my model's prediction. I can also turn on female and male group and say, for females, what are the top key important factors? Seems like marital status, sex, occupation, education, none are the top 4 important factors. That is a huge red flag to me, and especially the fact that males do not get anything here, meaning for males, their sex is not an important indicator of whether they get rejected or approved on the loan. And so I am curious to see how sex is impacting the model prediction. So I click here, and down there, let me see what I'm seeing. So I see sex on the x-axis, 0 being females, while being males in this data set. And on the y-axis, I see feature importance of sex towards rejection. And so for all of my females, the fact that they're a female plays a positive role towards class rejected. And for males, the fact that they're a male plays 0 role towards probability of rejected. So that's a huge fairness issue that I would like to investigate further with my fairness dashboard. But before doing that, let's go to local explanation. Switch to my female group. Here you can see that either a female group, you can go back and forth between any cohorts that you have defined. And by the way, each cohort can have multiple filters as well. So that's completely up to you which cohorts you would like to define. But in this case, I'm just gonna, for instance, click on this individual who is a female. She has been rejected by this model with 53% probability. And immediately I can see what are the top key important factors positively impacted that probability of rejection, and sex is the top one. So again, we have a huge fairness issue here. And I can do what if analysis on this data point and do like a little assessment test. What if this person was male? Immediately, in a hypothetical situation, I had the same person, just the gender was another one, a different value, in this case male. That person would have got approval for loan with 67% probability. Nothing about financial competency of that person has changed. So again, that is a huge fairness issue. I come back to my sample notebook and I continue with loading our fairness dashboard, passing sex and race as sensitive attributes to it. And so first, you are asked to specify what sensitive attribute you would like to move forward with. You choose sex. And how do you want to measure performance? For instance, say we choose accuracy. And so here we land on an exploration of how that model has done the job. The model is 84% accurate. I can see the accuracy broken down across groups. I can also see false positive rate, false negative rates broken down across groups. And so there is 12.3% accuracy difference between the female group and male group. Again, that is very, very interestingly explained by the lack of diversity that I had in my female group that I demonstrated in the Data Explorer. So majority of females had the ground truth of rejected. So even if model randomly rejects all the females, still it's going to achieve a high accuracy. But the thing that I care more about is the distribution of the favorable outcome or selection rate for loans. And so I can see that 24.9% of males have got approved for the loan and 7% of females have got the loan. And there's a difference between these two, which is 17.7% disparity in selection rate here, which I cannot tolerate. So I go ahead and I call grid search, which is one of the mitigation algorithms covered by and the labels and reweights is informed by this fairness constraint that we're passing. In this case, it's demographic parity, which truly is talking about this. It truly talks about the selection rate and the favorable outcome should be the same across different sensitive groups. And so I would fit my model again with respect to this grid search method. And I will load my dashboard again, but with variety of models that the mitigation algorithm has trained for me, pick the same configuration. And this time I will see a multi-model view to basically be able to compare my multiple different models and see how they stand with respect to accuracy versus performance. So now I can see that there are multiple different models that this has trained for me. I am very curious about this model. This is, by the way, performance versus fairness. So accuracy versus disparity in selection rate or disparity in predictions. I'm very curious about this particular model because it seems to have still a high accuracy, but a very low disparity in prediction, which is very nice with respect to fairness. So I click on it. And so I land on the landing page or on the result page of the exact same thing that I observed, but now for this mitigated model. As you can see, compared to the unmitigated model, my accuracy has been 2% lower. I can tolerate that. However, from almost 17.7% disparity in selection rate, now this model has less than 1% disparity in selection rate. And so that is something that I'm very willing to move forward and deploy because I could drastically improve the fairness of the unfairness of the model with respect to, or with using this particular unfairness mitigation algorithm. Now, the challenge is you might want to share these insights with other stakeholders. However, these are Jupyter widgets. And so that's where Azure Machine Learning comes into the scenario. Excuse me. And so you can connect to a workspace there. And after you're connecting to a workspace, you can basically register your models inside Azure Machine Learning. I'm going to demonstrate where they land momentarily. Upload your fairness dashboard, upload your model explanations, and that way, inside our web portal experience, you're going to see all of these insights attached to your model and ready to share with a variety of stakeholders. And so inside our web-based portal, you see all of your assets collected in one place, your data set, your experiments, pipelines, models, endpoints. And so I clicked on a particular experiment. This is experiment that I did and a particular one underneath that. And as you can see, there are a bunch of assets attached to that model. Explanation and fairness are both two assets attached. And so you can see the exact same dashboards that you just observed for both fairness and interpretability inside Azure Machine Learning Studio. And that enables you not just going back in time and looking at the model that you trained, like say 10 months ago or 2 months ago, and look at the fairness and interpretability insights of it, but it also helps you to share these widgets with other stakeholders who are part of your subscription, and in a way, make the informed decision in a collaborative way. Have all the stakeholders to decide which model is the best to go ahead and deploy. Coming back to my slides, I would like to talk a little bit also about FairLearn and where it stands with respect to adoption. And we are observing a very nice community being built around FairLearn with people with diverse backgrounds coming and helping us grow this community. And the interesting part is, of course, it is always hard to get adoption rates for open source packages, but we do know that it has been very well received beyond just Azure Machine Learning customers. And for instance, this table is from a recent study from researchers at the University of Cambridge who have highlighted that prediction practitioners and many people in the field rated FairLearn very high with respect to usability, and they found that educational materials that we provided were key to adoption of fairness in models and unfairness mitigation. And so if you're interested to learn more, definitely check out fairlearn.org and interpret.ml. And there are user guides and case studies attached to those. Now let's move on to some other toolkits that are out there. And H2O in particular is a great company that has an interpretability offering at training time, which is also a combination of glassbox model and black box explainers. And they also have auto reason code generation for local predictions, same as what we refer to as local explanation. And so a way for for a stakeholder to understand for each individual what factors are impacting the model's prediction. And so in their toolkit, there are a variety of different offerings under one roof, feature importance, SHAP values, all the way to surrogate models that also we support inside our Azure Machine Learning Interpretability package, things like decision tree, random forest, and also they have black box models like LIME. Then there is AI OpenScale, formerly IBM OpenScale, which with the goal to provide AI operations team with a toolkit that allows for monitoring and reevaluating machine learning models after deployment. And actually, this is IBM OpenScale. I mixed it with AI Fairness 360. But this is basically a cloud offering that IBM has, which enables you to monitor accuracy, fairness, and performance. And so there is a dashboard for each model that you deploy where you can see the health of multiple models side by side. And if there is any flag, that model will be tagged, for instance, as biased, and you can click on it and investigate a little bit further in terms of fairness over time, accuracy over time, and also robustness and performance of the model over time. And you can also take a look at and get a sense of the data set that was used to train that model and sort of get a sense as where the unfairness is focused and how well your model is making its predictions for different groups of people. Then we have AI Fairness 360 with 30 plus fairness metrics, 9 plus unfairness mitigation algorithms. They support a variety of pre-processing, in-processing, and post-processing algorithms, for the most part focused on binary classification case. And from Google, there is a very nice tool called Whatif Tool, which is sort of a code-free probing of machine learning models with respect to feature perturbation, doing what-if analysis scenarios, counterfactual example analysis similar to what Interpret ML covers as DICE. And also the focus has been on classification and regression. And for classification, they can show you and let you explore the effects of different classification thresholds and taking into account constraints such as different numerical fairness metrics. And so here is a quick demo of that we can quickly take a look at. So as you can see, you can click on any particular data point. You can do what-if analysis, hence the name is Whatif Tool. And you can see how the prediction would change and compared to the original data point that was like unperturbed, how that prediction would be impacted. You can also turn on the counterfactual example analysis and understand which point is the closest data point to that original point of selection, but with different outcome. And of course, you can also go to performance and fairness, and they support a variety of techniques where you can use, I'm not sure if that's going to play or not, but basically the way that it works is you will be able to assign different numerical fairness criterias, and in classification cases, the thresholds will be changed for each class, and that will help you achieve better fairness with respect to whatever constraint that you have specified by updating those thresholds. Eventually, governance and accountability are important facets of machine learning, responsible machine learning, responsible AI. And there are some very nice ideas out there. The first one being data sheets for data sets, which really suggest data scientists to accompany their data sets with better data-related documentation. Of course, we all know companies are dynamic. People leave teams all the time. And so if one data scientist have collected some data, there should be some documentation in place to communicate all the nuances and details of how that data sets have been collected, how it is supposed to be used, how it is absolutely not supposed to be used. And so the data sheets idea was born out of that every data set, model, or pre-trained API should be accompanied by a data sheet that documents its creation, intended uses, limitations, maintenance, legal and ethical considerations. And that was also expanded to the idea of model cards, which was taking it to the next step, that also when you train a model, that needs to be accompanied by an informational documentation that talks about the intended uses of that model, where it is supposed to be deployed, where it absolutely should not be deployed, uses to avoid, uses to that it's fine to have that model in that context, and any other data, including the architecture of it, the training data that has gone inside it, and any other materials that help the next data scientist to develop and deploy that model more responsibly. And eventually, the newest idea was FactChecks, that is distinguished from model cards and datasheets in that sense that the focus is in the final AI service and truly about the outcome and the how it is tested, or what test results were used on top of that, or to truly assess that model, and what type of intended use or intended impact that service output is envisioning. So with that, I will pass it to my colleague to walk you through Amazon SageMaker and the newest interpretability and fairness techniques out there. Thank you very much for your attention.
Hi, everyone. This is Krishna.
All right. Thank you so much for that the recording. And we are here in the flesh answering questions for you all. So we have a couple of questions we want to address really quickly before we move on with the rest of the presentation. And then I will ask if you could feel free to keep entering your questions, but we will hold off likely for the sake of time till the end of the presentation. So the first question that came out, I have from, let's see. All right, so first question is from Ms. Ganiet Kazim. I am curious as to whether your work and knowledge considers suitability and appropriateness in the context of understandability and explainability of use of AI. That is to say that there are often crossroads where we see tools that are cutting edge. However, their suitability may be questionable. So I don't know if you want to address that. Oh, I think you're on mute.
Yeah, that's
okay. There you go.
Always now. Okay, so I'm not sure if I understand that correctly, and definitely please reach out to me if I'm not getting it right. But so there are many variety of techniques. I assume that you're talking about how, like, they might disagree in some case. There are papers out there about the robustness of that, about whether those explainers are fitting the context and whether they're generating robust explanations. That is a true concern, and I don't believe that we have a best answer. From the research side, we're working on metrics that can evaluate how well the explainers are able to get the nuances of the model predictions and how well they're maybe even agreeing with each other. We have done a lot of benchmarking on them in case of how much they agree in terms of ranking of the top key important factors. We also have done work where we have fit an intrinsically interpretable model on top of the data. And so that model is intrinsically interpretable, meaning it's see-through inside out. And we then have run interpretability techniques on top of that in order to get a sense of whether what the explanation technique is generating as top key important factors is matching what the intrinsically interpretable model was picking as the top key important factors. But if you mean more in another context, like philosophical context, etc., I would love to learn more about exactly what that question means. There was another question about Nashli, about like lessons learned in the case studies that I got from you. There are many. There is a white paper actually. If you search for EY Microsoft FairLearn, there's a case study that I really recommend you take a look. One of the major things is no matter if you have access to sensitive attributes during your training time or not, you definitely, it is a best practice to bring them to the tool during assessment time, because no matter if you have used a sensitive attribute during training time or not, some other factors might have acted as a proxy into the world of fairness and leak information about fairness too. So don't feel like you can only remove sensitive attributes and call it a day. It's very important to always bring them, even if you have not used them, bring them during assessment time. So that was one major lesson for us, which actually was called out in our collaboration with EY. The other thing is, sometimes it's actually very, very easy to be misled by information of such toolkits like interpretability toolkit, fairness toolkits. Specifically in terms of fairness, it is important to look at the fairness at the intersection of sensitive features. For instance, you might see that, oh, for my females versus males, there is no disparity, meaning there's no unfairness observed. But when you dive deeper and you look at, say, white males versus white females versus black females, males, Asian males, females, you then understand that there are nuances, there are disparities, and there are unfairness or fairness issues that you're observing there. So it is important to have a process for impact assessment, clearly identify what are the subgroups that you want to understand, clearly identify what are the intersection of multiple features that you would like to investigate, not just one sensitive feature at a time, and then try to investigate fairness issues or even interpretations of the model on those cohorts. There was another question that was related to individual fairness versus group fairness, which I'm now going to connect it to the other questions about lessons learned. We also realized that while group fairness is super important, there is no guarantee that if we go through mitigation algorithms and we try to improve the fairness of the model on groups, we can guarantee that individuals are also getting fair treatments. And so it is important to bring a variety of techniques. That's why in the demo, I highlighted counterfactuals or also what-if analysis to get a sense of, now with this particular group, let's look at a handful of data points and try to manipulate or perturb their sensitive attributes and see whether they would get the same result. If not, then you know that you have individual fairness issues for some of the individuals as well, and you can go to some individual fairness techniques to hopefully mitigate that. And the last lesson that I want to highlight, and there are a lot more, but these are the key ones that came to my mind immediately, is the fact that it's always great to address the problem from the root. So if you have a fairness issue, always the best to go back to your training data, look at the balance of it, look at the characteristics of it, and if possible, not use the unfairness mitigation algorithm from the get-go, but try to use the data enhancements techniques first, try to address the problem from the very root, and then if none of those techniques work, or you don't have access to your data, or you can't collect more data, or you can't manipulate your data for any reason, then unfairness mitigation algorithms can be your best friend to help train a fairer or more fair model. Again, there are more. I'll be happy to chat with any individual, but yeah, I hope that I could cover a few.
Thanks, Mehernush. It has been really great. So given in the rest of the tutorial in the next 30 minutes, let's see, we will cover briefly some of the case studies from LinkedIn. This is work done while I was at LinkedIn, and then case studies from Amazon. So here here the focus was in a hiring setting, and as you all know, LinkedIn is very much in the hiring domain. So we were interested in understanding how do we reason about biases or fairness in this setting. And for us, the guiding principle was that we would like diversity by design. By this, we mean we do not want to build a separate product focused on, let's say, diversity in hiring, but instead integrate diversity insights into existing products. And diversity itself has been strongly motivated. There are several studies showing that diversity is tied to a company culture as well as financial performance. So in other words, we want to achieve diversity or fairness in ranking, not just for, say, some companies PR or other aspects, but also for its own. It's for the intrinsically good for a company to have diversity of experiences, of backgrounds, of skill sets, so on and so forth. So specifically, we looked at three aspects of planning stage when a company is interested in deciding where to source talent from. Then the hiring stage, where against a specific job posting, you would like to source candidates. And the third is development, such as diversity learning curriculum and so forth. I'm going to focus on the second one, because that's the part where machine learning models are involved. So here I'm showing a hypothetical mock-up screenshot of the LinkedIn recruiter tool, wherein a recruiter can search by title, skills, locations, and so forth, and they get to see a ranked list of candidates that match the query of the recruiter. What we ensured was that the ranking shown here for the top results is reflective or representative of the underlying talent distribution. This is a notion that we arrived at after collective discussion with all the stakeholders, including surveys to LinkedIn members, to LinkedIn's enterprise customers, as well as internal stakeholders. I'm going to briefly touch upon some of the motivation, but if you are interested in details, please refer our KDD 2019 paper, as well as an engineering blog post from LinkedIn. Here, the intuition is that we would like the top ranked results to follow a desired distribution on attributes such as gender, age, or the combinations. And one possible choice is that this top ranked result distribution should be the same distribution as the underlying talent pool. And there is a connection and an inspiration from the equality of opportunity line of work from the fair machine learning literature. So here I want to highlight that this is a classic example where there is a technical problem as well as a social or policy choice problem. And given that intrinsically this domain is socio-technical, at the beginning we were keen to identify the social and the technical aspects. So the technical problem was to design a ranking system and algorithm as a system that, given such a desired distribution as input, will achieve that. Whereas the policy or the social choice is what that desired distribution should be. And that can be that can range from ideal notions like demographic parity to the notion that we chose, which is the same distribution as the underlying talent pool, to possibly other notions. It's important to realize that, or acknowledge that desired distribution has to be chosen based on all stakeholders. It's not something that we as just people with technical background alone can decide. And that was the key tenet of this design as well. And once we had this intuition, we defined several measures of bias or skew or divergence based on this intuition. I won't go into the details, but intuitively these metrics capture the extent to which the distribution of the top ranked candidates differs from this ideal distribution. So ideally, we would like specifically this skew metric shown here to be close to 0. If it is positive, it means that there is over-representation of candidates in the top-ranked results, and if it is negative, the opposite. The algorithm itself is highly intuitively very simple to explain. the way it works is we take the set of candidates which are returned from the underlying machine learning model and partition these candidates into different buckets corresponding to each attribute value. For example, different buckets corresponding to different gender or different age groups, and then rank the candidates within each bucket respecting the score of the machine learning model, and then merge the ranked list wherein we balance the representation requirements and also selecting the highest scored candidates. In terms of how we do this merging, there are a few different choices, and that leads to a few different algorithmic variants. And we considered, we performed empirical evaluations of these variants and chose the variant which provided the best Pareto trade-off between the preserving highest scored candidates as much as possible and also achieving the desired representation requirements. So there is an underlying architecture which again it's discussed in more detail in the paper. So what did we achieve with this? First, we were able to ensure that nearly all the searches after this intervention are representative compared to the underlying qualified population for that query. And surprisingly, we also noticed that when we performed an A/B test, there was no significant change in the business metrics. The business metrics here correspond to notions like, is there mutual interest between the recruiter and the candidate in terms of did the recruiter reach out to the candidate and did the candidate respond back to the recruiter, which is considered a proxy for the likelihood of the candidate getting the job offer and joining the company. And since we did not observe any impact to the business metric, although we are imposing fairness constraints which deviate from just optimizing for business metrics, it was relatively easy to decide to ramp this intervention to all users of the LinkedIn recruiter tool worldwide. And what did we learn in the process? There are several lessons we learned. In this specific application instance, we learned that performing post-processing is desirable. It has a few benefits. The first benefit is that it's model agnostic, which means that it's scalable across different underlying model choices. At first, the model might be powered by an XGBoost model, and it can get changed to, let's say, a deep learning based model afterwards. Whereas since this approach is a post-processing approach, it's amenable to, or it's robust to such changes. The second is that it acts as a fail-safe. Even if by mistake or otherwise there is some bias which is present in the model, by imposing these representation requirements at the very top, we achieve the fail-safe property. And it's also robust to application-specific business logic or any other changes underneath. This doesn't mean that it's okay for the model to be biased or to have any biases. It's just that in the meantime, between any detection of such issues, we don't suffer from any biases in the end outcome. The third, from an engineering perspective, is that we chose the post-processing approach because it was easier to incorporate as part of existing systems as opposed to modifying the underlying components themselves, because we could even build a standalone service or component for such post-processing. And also let me note that this is complementary to efforts like what Mehanush was alluding to in terms of understanding any biases in the training data or even incorporating fairness constraints during model training. So all these are complementary and all these ideally should be adopted. And the most important lesson that we learned is that this is something that required inputs and also consensus across all stakeholders. Like if we poll, let's say, the attendees of this tutorial, we may all agree that notions such as privacy is very important, but we may disagree on, let's say, the trade-off between privacy and preserving accuracy of a model. But if we consider notions like fairness, there is very likely that we may not even agree on a common notion of fairness. There are tensions between individual and group fairness. and there are tensions between even theoretical impossibility results on simultaneously achieving multiple competing fairness notions. So because of all such factors, it is very extremely important that we do not look at this as a purely technical problem, but loop in all the relevant stakeholders. And that's a lesson that that resonated across all the such all similar or other deployments of fairness notions across many different companies. So once we did this, so before that, if you're interested in more details, this is the paper. It has a detailed description of the algorithms, the trade-offs, lessons learned, experimental results, and so forth. So why? So given this, what did we learn in the process? We then also learned that it's often not enough to just compute the bias measures, but also to understand whether there is statistical significance of this measured discrepancy. And this is a work that we subsequently adopted, and this is the details are there in a KDD 2020 paper. The idea is to use statistical hypothesis tests, and specifically use a type of non-parametric test called permutation test. There are a few challenges with just using the vanilla version of the permutation test, but turns out that there is a way to apply a technique called studentization and achieve the desired outcome in this setting. I'm going to skip in the interest of time, and then go to something what we then proceeded further. Having chosen one application, specifically the hiring application, we took a step back and wanted to understand how do we design mechanisms for measuring biases and mitigating across the entire machine learning lifecycle. And then we went about building a toolkit for achieving this. And subsequently, this was open sourced by LinkedIn as well as LinkedIn Fairness Toolkit. Here, the intuition is that we want to address bias-related issues at different stages, ranging from biases in the training data to biases or fairness constraints during model training to measurements post-model training, as well as even once the model has been deployed in production. Specifically here, we were focusing on how do we design such a toolkit to be flexible to be flexible to be used. It has to be available for use as part of, say, ad hoc exploratory analysis using, let's say, a Jupyter notebook, or it should be usable as part of offline workflows, or even integrated with proprietary ML frameworks that may be used in a company setting, like in LinkedIn. The second requirement that we had was that it has to be scalable. When we looked at many of the available open source toolkits, we noticed that all of them were designed to be run on a single machine or single instance, whereas the use case at LinkedIn involved running over possibly tens of millions of user data, or perhaps data spread across several machines. And so we needed a scalable approach which can be run in a distributed fashion. And in addition, we also incorporated several different fairness metrics, including custom metrics that can be specified by the user in the form of user-defined functions, because we may not be able to capture all possible fairness metrics. More details are there in the paper here. Please take a look if you're interested. And let me thank that this is joint work with several former colleagues at LinkedIn. And with this context, personally, like I took the next step in terms of, at LinkedIn, I was able to start with the hiring motivation, and then looked at addressing biases across all LinkedIn applications. How do we go beyond one domain, like hiring or professional network space? And that's what we started looking at Amazon. And specifically, in December of 2020, we launched a functionality called Amazon SageMaker Clarify as part of SageMaker, which is the machine learning platform that Amazon offers. Clarify is a tool to help detect bias in machine learning models, and also understand the model predictions and explain model predictions. As some of you may be aware of, Amazon SageMaker is a machine learning platform. It's being used for a wide range of applications, ranging from fraud detection, predictive maintenance, or churn prediction, computer vision, autonomous driving, or financial applications, and so forth. And what we added here was functionality on bias and explainability. So specifically for bias, often customers may not understand whether there are any biases or imbalances present in the data set, or whether biases are developed during training. And similarly, like, are there any biases present once the model has been deployed? And this is very important. It's not just enough to measure biases on the data set or while the model is being trained, but also monitor over time. Similarly, like in terms of explainability, the motivation was that the machine learning models have been becoming more and more complex and opaque. So from various needs, we would like to both explain the behavior of the model as a whole and also explain the individual predictions made by the model. So with this context, what we offered in SageMaker Clarify was different functionalities to identify biases at the time of training data preparation, to check the trained model for bias, and also to explain the overall behavior of the model. And then once the model has been deployed, we wanted to explain individual predictions in terms of which features are most important for a specific prediction, and 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 also detect any drifts in the bias and model behavior over time. These such drifts can occur due to possibly changing real world conditions, and in those cases we wanted the customer to be able to get alerts and take corrective actions as needed. These actions might involve retraining the model, or perhaps looking at what's causing these biases. Are there any bugs introduced? Are there any assumptions that are no longer valid, and so forth? And finally, also help generate reports which they can share with other internal stakeholders. And this is, we designed this. One of the lessons we learned in the process was that instead of offering as a new service or functionality, we decided to integrate this into the respective parts of the machine learning lifecycle. Specifically, we integrated this as part of the data preparation stage, also called the SageMaker Data Wrangler, so that we can measure biases at the time of the training data preparation. Similarly, like at the time of training and tuning the model, we also provide a way to measure the post-model training biases. Is the model having similar predictive behavior across different users? Yeah, and similarly, like the behavior of the model as a whole. And then once the model is deployed, we using SageMaker Model Monitor, we integrated the functionality for detecting drift in bias as well as explainability over time. So let me show you a quick walkthrough of this functionality in terms of a case study over a publicly available data set. Here we are going to show the a case study over German credit data set. The very first step is we need to import the data set, and we're going to import the German credit data set, which contains information about individuals and whether they have good credit or bad credit. And once this is imported, the next step is to create a type of analysis. And in this case, we are adding an analysis which is bias analysis. And for this analysis, what we want the user to provide is the user needs to provide which column corresponds to the label and which attribute we want to measure bias against. For example, the column that corresponds to the label here is whether the person has good credit or not, and we also need to say what is the corresponding value, and then we want to measure biases with respect to age, whether there are biases between those who are age 40 and above, or age less than 40. And once this is done, we can select from a set of different bias metrics, and then then in near real time, we can compute the corresponding metrics, the bias metrics on the training data, and then likewise, once the model has been trained, we can also then go and compute the bias metrics of the trained model. And for each of these bias metrics, a lesson we learned is that it's important to present intuitive examples. There are a wide spectrum of customers, ranging from highly sophisticated customers who may be familiar with who may have in-depth familiarity with the fairness literature and machine learning, to the customers who may be, say, product managers or business leaders who may not have as much familiarity with machine learning or fairness. So we needed to cater to this wide spectrum of customers. So we had to provide sufficient intuition, sufficient explanations, examples of these metrics and so forth. So here we are showing what happens at the time of training. So this is using what's called a SageMaker processing job. And here the user has specified what bias metrics they want to compute. And then as part of the processing job, in addition to other metrics like accuracy, error, and so forth, we also compute bias and explainability related measures. And then once these are computed, these can be visualized from inside SageMaker Studio, which is a visual integrated development environment for machine learning. And the user can look at a specific machine learning model that was trained uh, and visualize which are the most important features, as well as visualize which are the values of the various bias metrics. And then depending on those values and where they are in terms of the allowed range and what is acceptable for the specific application need, they can decide whether to take corrective actions or not. Let me move to the next part, which is what happens once a model has been deployed. So here we are going to an endpoint which corresponds to the deployed model, and we are looking at we are picking a specific model endpoint, and we want to understand whether there are any biases or explainability drifts after the model has been deployed. And here, as part of model monitor, we can monitor the model at regular intervals. These are specified by the customer depending on their need. This can be, say, every hour or every day or every week and so forth. And what we show here is, are the top features stable over time? Do they agree with what is the expected behavior? If, for example, if it turned out that the past credit behavior or past repayment of loans was the most important feature at the time of training, but once the model has been deployed in production, we are seeing some other feature as being important, maybe the location or other features which may be possibly like indicators of any bias, then that becomes a red flag. And that's something for the machine learning practitioner to go and visit and check whether the model is behaving as expected. And here we can also see how the importance of each individual feature changes over time, as the distribution of the data might possibly change over time. And the next, similarly, like we can also monitor whether bias is occurring over time, even though there may not have been any bias at the time of the trained model, or the bias might have been within acceptable limits for this application. Once a model has been deployed, because of unseen examples or because of change in the data distribution, it's quite possible that the model might start behaving in a biased manner. There may also be feedback effects in case the model is leveraging the user feedback signals, and that can also lead to possible biases. So this hopefully provides a overview of some of the functionalities here. So with this background, I'm going to just go into what did we learn here. A key lesson we learned is that fairness has to be thought of as a process. The notions of bias and fairness are highly application specific, application dependent. So this means that both the choice of the attribute for which we want to measure bias, as well as the corresponding bias notions or metrics, have to be guided by the social, legal, and other non-technical considerations. And these often are, as we discussed at the beginning earlier in the context of a question, these are often industries dependent or the application dependent. Yeah. So since we designed a toolkit or functionality as part of SageMaker, we let the customer make these decisions. We provide a set of bias metrics that cover a broad spectrum of different use cases and let the customer choose which is the most relevant for their application setting. The second lesson, again, I won't repeat this, it's that it's very important to take inputs from all relevant stakeholders into account, and to accept that, or to be cognizant of the fact that bias is not limited just to the machine learning lifecycle. It can be beyond that. It's not just confined just to the data model or model predictions. It's even beyond that. It's very much part of how we even start addressing or asking questions, how we start involving all stakeholders from the very beginning, and so on. So I think I discussed this already, which is that we want to cover customers with different levels of technical background. This is where customers find it beneficial to have a managed service as opposed to having to go and find out which is the relevant open source package, tune the parameters, figure out how to invoke those open source packages, what's the right way to use them, and so on. So this is a difference that we are noticing. This also relates to the machine learning ops that we discussed earlier, wherein there is benefit of offering such functionality as a managed service as opposed to the customer having to figure out on their own by using, say, many of the, or one amongst the several open source packages. And the other lesson is that it's important to look at bias and explainability for the monitoring as well, not just at the time of model training. So with that leads naturally to looking at fairness or explainability considerations across the entire model lifecycle. So this includes yes, starting with problem formation. We need to ask, is an algorithmic approach even an ethical solution to this problem? Then at the time of data set construction or model training, again, we need to ask whether we have is the data representative of different groups or their biases. Do we need to apply bias mitigation techniques, and so on? And then similarly, like, has the model been evaluated using relevant metrics? Are there unequal effects across users? Are there feedback loops that could cause increasingly unfair outcomes? All of these need to be thought about while applying such solutions. So if you're interested in more details, there are a few blog posts and a technical paper linked from the SageMaker Clarify webpage. We also have a systems paper on the SageMaker Clarify, which is going to be available shortly. I would like to thank all the team members and partners for making this happen. So in the interest of time, I'm going to skip the details of a related tool called SageMaker Debugger, which is a tool for understanding or debugging while the model is being trained, a tool to help the data scientists and machine learning practitioners get real-time insights while the model is being trained. And if you're interested in details, there is a paper that is going to appear in the MLSys conference a couple of months from now, which has the motivation and details of this. Let's see. So I think we're running behind in terms of time, and so because of that, let me go to the takeaways, and let Nashley present some of these takeaways.
Yeah, so we have maybe like 1 minute, so you can just keep going to the next slide. And for those of you all who didn't get your questions answered, please feel free to reach out to each of us via LinkedIn or Twitter or anything like that. We also want to make sure people are thinking holistically about these products. We don't want to keep you all too long, but please do check out the extended version of the slides. They are posted from the AAAI conference as well. And I'm sure these will be available for playback as well. So thank you all. Anything you want to add, or if not, thank you all for tuning in. We appreciate it.
So just one note I would like to add in addition to what we discussed is it's good to think in terms of what's called the front page newspaper front page test. Is that irrespective of how underneath or deep beneath we may be working on say machine learning or AI settings, it's a good question to ask ourselves, if there is a media article about what we are doing, would that make us uncomfortable? If that's the case, it's a good time to pause and ask whether we need to measure biases, whether we need to incorporate privacy tools or explainability tools or other reliability, robustness, safety, and those kind of considerations, and start the conversation with the relevant stakeholders. And these stakeholders have to include people beyond just the computer science or technical disciplines, from social science, policy, ethics, legal, and several other backgrounds. And with that thought, I'll conclude. And all these links, there are a lot of extensive related tutorials, resources, which are linked from the tutorial webpage. And please reach out to us if you have additional feedback or questions. And looking forward to continuing the discussions on the Slido chat, as well as hope you all have a great rest of the FACT conference over the next several days. Thank you all.
Bye-bye. Thank you, everybody.